Another method of detecting exoplanets is called the transit method. And this one is fairly straightforward. What it does is that we take a look at the star's light and we look at what happens as a planet passes in front. Now, of course, this necessitates that the planet and the star are aligned. Again, we talked about this before, like if you're in the right sort of plane. So if you're sort of looking at this right here, and this right here is your star, and this right here is your planet going around, it has to be in the same sort of orbital plane here. If this is like your piece of paper, where everything is sort of sitting on this two-dimensional flat piece of paper, it has to be where it passes in front. Because if I took this piece and I sort of rotated it 90 degrees, well, that would be really bad for us because, let me just attempt to do that. I'm not sure if I actually can here. Yeah, I think I can. I can go like this. So let's say if it was orbiting like, back and forth like this right here, we wouldn't actually see this effect happen. So that is going to be really important, that we have to be lined up. Now, this is a real picture taken with a cool filter, though. This is the sun with the planet Venus passing in front of it. So someone decided to take a really cool picture of this. So this is the sun with cool filters, so that way you can sort of see what's going on the sun here. But if you look at it as Venus passes in front, then what's going to happen is the light from the sun, there'll be a little bit less because it's a little bit darker. You see, the planet doesn't actually give off much light. It reflects some light, but it doesn't really emit much. So overall then, if you have a planet in front of a star, it should dim the light. The light should actually be a little bit less. Now this is extremely small effect. Again, this is really, really small. I mean, look how small this planet is compared to the size of the sun. So this is an effect, though, that's going to dim the light from the star very, very little. Obviously, if it's a bigger planet, let's say the planet was like this big, and then it passed in front of the star, then the star's light would dim a lot more. See, it all depends on the size of the planet compared to the size of the star, and we'll see how much then that the light dims. So it's a pretty straightforward idea. First of all, we graph the star's light intensity versus time. Remember, we can't actually see the planet. See, like this right here with the Earth and Venus, that we can see because Venus is in our own solar system. It's so close we can actually see it go by. You see, we can see this little circle go when it drives by. But with exoplanets, these stars are so far away that these unseen planets going in front of them, we can't actually see the planet itself. So you can't just take this kind of picture with another star. The reason is that you'll never see this planet go in front of it. That star is just a little dot of light. You can zoom in, it just becomes a brighter looking dot. You won't actually see sort of a thing with features, at least not easily. So then what we do then, we graph the star's light intensity versus time. So imagine this right here, we're going to do a graph right here, and this right here is time. Okay, so this is like 0 time, this is more time here, so this is, longer away. And this right here is going to represent the star's intensity in some way, so how bright the star's light looks. And let's just say over time it does this. All right, nice and constant here. So let's just say over time, as time is 0, then the intensity is some value. And if you wait a little bit longer, the intensity of the star is still the same. Come back a little bit later, still the same. So this is not an exciting star. This is a star that's just a regular old star. But what happens then is this. If a planet does pass in front of the star, it can dim the light. So this is the intensity or brightness of the star. As the planet passes, so this, for example, right here, this represents, see how the planet is not in front of the star? This is the star here, this is the planet. So right now, the planet is not in front of the star, so that's why the star's light is still bright. But what happens as the planet passes in front of the star? It blocks out or occludes some of this. So when it passes in front, we call that a transit. That's when it transits, it passes in front. So as it passes in front, there's less light received from the star, so therefore the graph of the brightness of the star will all of a sudden drop down to some value and then go back up again, as it, of course, is no longer in front. So we're looking for these periodic dips in the star's light. If we see these, then and if we see enough of them, then we can tell that it's an exoplanet. Now, some stars can actually have their own brightness dip, So some stars are actually variable. So this complicates things a little bit, and that's a reason, and some other reasons as well, why the transit method is okay. It's actually very quick to do, but the issue is it's not all that reliable. So what we often do is we often confirm transits with the radial velocity method. So the method that I showed you before is usually the way to sort of confirm that it's really a planet and not something else. Because there's some other effects that can make the star's light dim. There's some kind of cool things, though, that actually if it's a real exoplanet, you'll see it dim periodically, first of all. But also you'll see dips, and you'll see dips of different sizes. And there's some weird things going on. But the main idea behind it is that you look for the light of the star to dip and then go back again. And that tells us that a planet likely passed in front of it. So what can we infer? What can we tell from this? Well, first of all, these are real graphs, by the way. This is one called Kepler 20e. This is another one called Kepler 20f. So this tells you that that first of all, there's a star called Kepler 20. It has another name as well, but this is a particular star being looked at by a satellite called Kepler. So it's actually up in orbit around the sun, not around the Earth. And this one here has been taking pictures of a bunch of stars. We're going to talk more about this project later. But there's, the 20th confirmed one, so it's called Kepler 20, and that one has multiple planets. That's why I remember the first planet will be called B, then it'll be called C, then D, then E, then F. So look, this one has multiple planets around it. Now, this is the real graph. This is flux. This, again, just tells you amount of light, and this is also the time from mid-transit. So this just tells you something about the time here. So what it tells you basically is that the amount of light from the star, it dips down and then goes back up again. But look how messy this is. This is the real data. Now they take these, they put them together to make little data points. They have little up and down arrows to tell you a little bit how unsure they are. But really, you do see this plot. It's a bit fuzzy, but if you do these enough times, you get enough data, you can actually tell statistically that this really does go down. It's not just a weird blip in these dots here. So this is what the real graphs look like. They're not as pretty as what I showed you. In theory, it could look like this, but in reality, a lot of them, they look like this. They're a little bit messy. But what can we tell? Well, it turns out by knowing this right here, this depth of the transit, and if you know the transit time, so those are the two things. You can tell sort of how much it dims the light, and you can tell sort of how long this transit lasts. You can tell some things. I mean, one of the things that you can actually tell, you can tell actually the planet's radius. So that's really cool. And what I mean by that is that, and also you can take the spectrum of the light. So also what you can do, this is I think the coolest part about this. So first of all, you can tell the planet's radius in a sense. You can tell how big it is compared to its star. And another really interesting thing you can tell is if you take a spectrum of this star's light. So if you take a spectrum of this right here, like we were learning before about a spectrum, how you can take the light and break it up into different components. And if you look carefully at the spectrum of the star, you see these lines, let's say, like we were learning before. This is the wavelength, that's lambda. If you can take a spectrum of the star, what you do is you look for these lines of the star, and so you'll see that'll tell you really what the star is made of. Okay, but during the transit, when this planet passes in front of the star, so right here, during this time right here, take a whole bunch of spectrums again, and if you see extra lines, you can tell what is in the planet's atmosphere. So if the planet has an atmosphere, you could tell what's in it. So in other words, if this exoplanet has gases around it, then by taking a whole bunch of spectrum of these stars' lines, you might all of a sudden, when it's passing by, you'll see extra lines. That'll only be here during the transit, and then those lines will be gone again. That's actually because some of the light from the star passed through the planet's atmosphere and reached us, and we can detect it using a spectrum. And believe it or not, they've done this. So scientists have just started to detect exoplanet atmospheres. Isn't that amazing? So these alien worlds, we can tell their radius, we can tell what's in their atmosphere if we can take a sufficiently good spectrum of them. And if we take the radial velocity method, we can tell also the distance from its star, so we can infer something about the temperature of the planet, and we can tell something about the planet's mass. So with these two methods, we can tell a lot. I think that's really, really interesting. And again, we usually confirm transits by the Doppler method. And one famous experiment or one famous mission that's currently underway is done by NASA, that's the American Association, and this is called Kepler. So Kepler's been up in orbit for a couple of years now. And what it's been doing is it goes around the sun and it's staring, unblinking, at the same spot in the sky. Now what it's doing is it's trying to detect if there are exoplanets around a bunch of other stars. But rather than look at just the light from one star, it's looking at hundreds of thousands of stars without ever blinking. Its mission was designed to be 4 years. And the reason they do this is because if it's an Earth type one, it only passes in front of its star only once every year. So that means that we'd have to see, it turns out we want to see at least 4 of these right here in order to really tell that it's an exoplanet. Turns out the more of these you see, more of these you sort of detect, the better. So the idea was, all right, let's try to detect Earth-sized or at least Earth orbit, Earth-type orbit transits. So we could do that by, if we stare unblinking at hundreds of thousands of stars for 4 years, we should be able to catch at least 4 of these transits of these really interesting types of planets. Obviously, the ones that are really, really close, they're going to transit really often. Some of them transit only every few days, like hot Jupiters, like I was talking about before. Large planets that are really, really close to the star. Those will be easy to see. We'll see these transits happen every few days. We'll see like boink and then another one. So these hot Jupiters are easy to detect. But the ones we're trying to detect are ones that are harder. So ones that only pass in front for, maybe just a few minutes or a few hours out of an entire year. So that's why you have to stare unblinking. So you have to go into orbit. You can't just be on the Earth looking because maybe it's dark or it's night or there's clouds. So that's why they have this mission called Kepler, and it's staring at the same place in the sky. Now, unfortunately, Kepler just had some problems. One of its motors isn't working, so there are actually some issues with Kepler at the moment. So it's a little bit scary. We're not sure if it's going to work, but it has detected thousands of these. So still, we're looking at lots and lots of data. We still have to crunch tons of data in order to even figure out what Kepler found. So this Kepler mission, if this is our galaxy, this is again just a diagram. This is roughly where it's looking. So it's looking in this area here of a distance of about 3,000 light years. Remember what a light year is, the distance that light travels in 1 year. So it's many, many, many hundreds of thousands of kilometers, or many millions, in fact. So its distance, the search area, is only this tiny little piece right here. That's it. And it's already found thousands of potential ones. Now, when I say potential, that's because a lot of them, they have to be double-checked. So they're going to double-check a lot of them. They're called, the interesting ones are actually called KOI. These are Kepler Objects of Interest. So if you're looking in a database, you see KOIs. These are things that are interesting that Kepler thinks it found an exoplanet, but you have to confirm it. So we normally use the radial velocity method to make sure it's really an exoplanet, because some of them aren't, but most of them are. So that's another method, is this transit method. And it's really cool because we're getting tons of data coming in from Kepler. So even if it stops working, which it seems to have, we've still got lots and lots of years of analyzing the data to figure out what there was. Now, direct imaging is another way of doing it. And this is insane. When I really first read about this, I thought this would be completely impossible. You'll never be able to take a picture of a planet. That's because it's just too far away. But it actually is. By really pushing the technology, by really, really sort of advancing technology and processing the images quite seriously, they have actually been detected. So this is what we do. We take a picture. Well, first you have to choose a star to image. Now, normally it looks too bright. So what I want to show you is this. Let's pretend that I'm driving my car here. So let's say this is like a view of what I see when I'm driving my car. This is the steering wheel here. So there would be me driving my car. This is my rear view mirror here, sort of in the car here. I'm a really bad artist, you can see. So this would be my hand here. So maybe I'm, let's see, I'm like this. I'm trying to drive my car here. There we go. So this is me. That's my hand. Now, what if the sun is in my face? Have you ever had this? Like if you're driving in a car, even if you're biking or something like that, like the sun is just really, really bright right in your face here. So while you're trying to drive, it's really, really bright. The sun is so bright. So what do? You put your hand in front of you. At least I do that sometimes. So actually, I just put my hand in front of the sun, and it sort of blocks out the sun. So see, that's sort of what I do at least. So this is sort of a view. I sort of put my hand out in front of me. Imagine me doing that. I sort of block out the light from the sun. That's essentially what we're trying to do in this method here. So we first choose a star to image, but the star looks too bright. So we need to put something in front of it. So we put a cover over the star. It's called a coronagraph. And this is an example of our own sun. And what they've done here is they've actually put a coronagraph in front of it. So this is a NASA mission where what they've done, they've actually this is essentially putting your hand in front of the star. So this right here, this is just a shadow here. This is like your arm. So this is the arm for the little thing that's blocking out the light of the sun. This right here shows the actual size of the sun. So the sun's only like this big right here. So this right here, this is or sometimes it's a center. I've seen some of them and actually shows the size. Some of it is just a center. But in any case, the idea here is we block the light of the sun. Now this one right here was done in order to check for coronal mass ejection. So the star kind of burps out this magnetic material here. So the star, our own sun does this all the time, and we think other stars do. So we know a lot about other stars by watching our own sun. But see this idea though, that if you can block out the light from the sun, then maybe you can tell something. So an extreme case of that though, imagine though this star is super duper far away. You try to do the same thing, and then you try to look for planets orbiting around. Now this is really pushing the limits of science and technology. This is extreme image processing. So this one here is a star called Fomalhaut. And that one, for example, from the Hubble Space Telescope, they took some images. Now, you might think this looks like from like Lord of the Rings, the Eye of Sauron, and it's not, although it looks like it. This is just, what they've done here is here's the location of a central star. This is the coronagraph mask, so this is sort of the cover here. Okay, so ignore this completely. Now there's a lot of scattered starlight noise. This is just because they've taken lots of pictures and really processed the picture. So try to ignore these weird dots here. Those are actually not important. Those are artifacts. That's like if you take Photoshop and keep messing around with the pictures, sometimes you get lots of extra pixels and extra sort of what we call noise. So try to ignore that stuff. This dot right here, ignore that. That's a star behind. So that's just a background star. But the reason they were doing this was to try to look for this dust ring. So you can see there is some material over here sort of going around the star. So they were trying to look at, this is maybe how stars are formed and how solar systems are made. So there's some extra dust left over and maybe there's some planets. Well, look carefully at this little dot right here. In 2004, they took this picture and it was here. 2006, it was here. They've actually taken this picture since, and it's actually moved a little bit further. And this orbit, if you actually sort of draw the path of it right here, you can actually do that. And you can draw the path, and it's in what we call a nice Keplerian orbit. So it follows Kepler's laws. What this means is that there's a real object in a real gravitational orbit going along. So this is considered a planet. So these little dots right here, that was one of the first, there's been others, but this is at least one of the more famous ones of doing direct imaging. Now, like I said, it's really pushing the limits of technology, but it's happening. It's starting. So they're starting to do this, which is so cool because if you could do this, and if you could take an image of this, what if you could take the light from that the light from that planet? Because see, the star is getting a lot of light onto that planet, and that planet's reflecting it, and that's reaching us. This is an amazing feat of technology here. But if you can take that light from that planet then, and if you could focus well enough on this one little piece right here, okay, if you could actually get, let's say it's sitting right here, and you took a really good quality picture of this particular dot, then you could tell about this planet. So you could again do a spectrum, and this spectrum could again tell you what's in the atmosphere. So if this planet has an atmosphere, you could see these sort of spectral lines like this right here. You could tell what this planet has in its atmosphere if it has one. So maybe it has oxygen. Maybe that tells us that there's, at least more interesting place to look for life. So this has really interesting results for us and really interesting implications.